Analysis model. Traveling wave. In this session, we will explore the traveling wave analysis model. Our discussion begins with an introduction to how traveling waves function and the specific properties of sinusoidal waves. We will then examine the mathematical representation of these waves, including the relationships between wave speed, frequency, and period. Finally, we will look at how to calculate the transverse speed and acceleration of the individual elements within the medium through which the wave travels. The traveling wave model describes a disturbance that moves through space without interacting with other waves or particles. A simple way to visualize this is by imagining a pulse created by shaking one end of a rope. If you shake that rope continuously using simple harmonic motion, you produce a sinusoidal wave. These sinusoidal waves are the most basic examples of periodic continuous waves, serving as the fundamental building blocks for understanding more complex wave behaviors. It is crucial to distinguish between the motion of the wave itself and the motion of the elements within the medium. In the diagram, the entire waveform moves to the right at a constant wave speed. However, an individual element of the rope, like a single point on a string, only moves up and down along the vertical axis. This vertical movement is simple harmonic motion. While the wave progresses horizontally, the physical particles of the medium simply oscillate about their equilibrium positions. To describe waves accurately, we use specific terminology. The highest point of a wave is called the crest, and the lowest point is the trough. The wavelength, represented by the Greek letter lambda, is the minimum distance between any two identical points on adjacent waves, such as the distance from one crest to the very next crest. The amplitude, labeled as A, represents the maximum displacement of an element from its resting position. These physical dimensions define the shape of the wave in space. Two other vital parameters are period and frequency. The period, denoted by a capital T, is the time interval required for one element of the medium to complete a full cycle of oscillation. It is also the time it takes for the wave to travel, a distance of exactly one wavelength. The frequency, denoted by F, is the number of crests that pass a fixed location per unit of time. Frequency is the inverse of the period and is measured in hertz, where 1 hertz equals 1 cycle per second. We can represent waves using two types of graphs that look similar but show different things. A snapshot graph plots the vertical position against the horizontal position at one specific instant in time, showing the wave's shape in space. A position time graph tracks the vertical movement of just one single element over time. Both graphs have the same sinusoidal shape because the wave is a function of both position and time, reflecting the repetitive nature of the motion. To represent a wave mathematically, we use a sine function. For a wave at time 0 traveling to the right, the vertical position y is equal to the amplitude a times the sine of the quantity 2 times pi divided by the wavelength, all multiplied by the horizontal position, x. At any later time t, we account for the wave's movement by replacing x with the quantity x minus wave speed times time. This formula allows us to calculate the displacement of any part of the wave at any moment. We often simplify our wave equations by defining specific parameters. The angular wave number k is defined as 2 times pi divided by the wavelength. The angular frequency omega is defined as 2 times pi divided by the period, which is also equal to 2 times pi times the frequency. Using these, the wave speed, v, can be expressed in several ways. Wavelength divided by period, wavelength times frequency, or angular frequency divided by the angular wave number. The compact form of the wave function is the vertical position y equals the amplitude a times the sine of the quantity angular wave, number times position, minus angular frequency times time. If the wave does not start at 0 at the origin, we add a phase constant phi inside the sine function. Note that while a minus sign indicates motion to the right, A plus sign between the position and time terms indicates a wave traveling to the left. Let us look at a practical example. We have a wave moving in the positive x direction with an amplitude of 15 centimeters, a wavelength of 40 centimeters, and a frequency of 8 Hz. First, we find the wave number by dividing 2 pi by the wavelength of 0.4 meters, giving 15.7 radians per meter. The period is the inverse of the frequency, resulting in 0.125 seconds. The angular frequency is 2 pi times 8 Hz, or 50.3 radians per second. Finally, the wave speed is wavelength times frequency, which equals 3.2 meters per second. This sequence of images shows how a wave propagates over time. At time 0, a crest is at point P. After 1/4 of a period, the crest has moved to the right, and the element at P has moved down to the equilibrium position. By half a period, the element at P is at a trough. The transverse speed represents how fast that specific element is moving up or down, which is found by taking the partial derivative of the wave function with respect to time. The speed at which the medium moves is different from the wave speed. The maximum transverse speed is equal to the angular frequency times the amplitude, and this occurs when the element passes through the equilibrium position at y equals 0. The maximum transverse acceleration is the angular frequency squared times the amplitude, occurring at the maximum displacement points. While the wave speed remains constant in a uniform medium, the transverse speed of the elements changes sinusoidally. In summary, the traveling wave model describes a disturbance moving at a speed equal to wavelength times frequency. Sinusoidal waves are mathematically described using amplitude, wave number, angular frequency, and an optional phase constant. It is vital to remember that the elements of the medium oscillate in simple harmonic motion, which is distinct from the wave's translational motion through space. Lastly, the wave speed depends solely on the physical properties of the medium itself. To wrap up, consider these review questions. First, if the frequency of a wave on a string is doubled while the tension and mass density stay the same, how does the wavelength change? Think about the relationship between speed, frequency, and wavelength. Second, can you explain the physical difference between the wave speed and the transverse speed of an element? Understanding these distinctions is key to mastering the traveling wave model.